Recording in progress.
The Yefimov phenomenon with finite range interactions, while thus far the stress was more on zero range interactions. And I think it will be very interesting to see how much of the nature and the magic of that phenomenon is still visible with finite range interactions. So and please ask questions through the chat, and don't feel discouraged even to speak up orally. That would be fine too. Okay, yeah, please.
Any questions are welcome. Okay, so let me. Can you see the screen? Yes.
Yeah.
So before I start today's lesson, I just wanted to say something about the yesterday's lesson. For those of you who could attend it, we saw the Born-Oppenheimer approximation, and then I received an email by Jean-Marc Richard, who made a very interesting remark that actually what I presented can be very simply improved. So I just wanted to show this point briefly. So yesterday we saw the Born-Oppenheimer approximation for this two heavy particles with a light particle. And I went very quickly. I said that we can first solve the problem for the light particle and then the problem for the heavy particles. And implicitly what I did is that I assumed that we could separate the coordinates of the system in the following way. So first we separate the center of mass of these two heavy particles, and then we have the relative coordinate for these heavy particles, this capital R, and then we have the coordinate for the light particle. And so in this way, so then I neglected the center of mass, and we just had these kinetic energies for the heavy particles. This is relative motion for the heavy particles, and kinetic energy for the light particle. But actually, it turns out that a more accurate way is to first eliminate the center of mass of the whole system, not just the heavy particles. And then if you do so, you still have the relative motion for the heavy particles. That doesn't change. But then for the light particle, what enters is actually the relative motion between the center of mass of this two heavy particles and the light particle. So the only difference is now that we have the reduced mass between the two heavy and the light particle, which is given by this expression. So 1 over mu is 1 over 2m plus 1 over m. So that's a very small change, but then everything looks the same, what I showed yesterday. The only difference is that instead of m, we have the reduced mass. And then I looked at this critical mass ratio in the systems of two identical fermions, two polarized fermions interacting with a light particle. So in the Born-Oppenheimer approximation, we estimated the critical mass ratio beyond which the Yefimov attraction wins over the centrifugal repulsion. And we obtained this result. So from this formula, 13.99, and I said it's very close to the exact result, 13.6. But actually, if we now take into account this what is it called, reduced mass, then we get a factor, a term 1/2, an additional term 1/2, and which gives the results for the critical mass ratio of 13.49, which is actually much closer to the exact result. So that's a very simple modification of this Born-Oppenheimer theory that gives a more precise result. So I think it's worth. So I'd like to thank Jean-Marc for pointing out this nice point. Okay, so I'm just
Pascal.
Yes.
I mean, it was good that you brought this point again. Indeed, I had a question yesterday, but I mean, there are so many discussions. So I just thinking, I mean, looking to this figure you have, two heavy and one light. And just think about that you put another light
Yes.
that do not interact among them.
Yes.
I think this is also a very simple example that
Yes.
you can treat. And
Yes.
essentially, I think your omega
Yes.
is changed, no?
Yes.
And this is what I wanted you to comment, because this is, I mean, from the conceptual point of view, is quite interesting, because you have the ephemeral factor for two heavy and one light. Then you put another light that do not interact with, just interact with the two heavy.
Yes.
So your simple formula that we see on the slide, just omega is changed maybe by a factor of 2.
That's correct.
I don't remember, a square root of 2.
Yeah, factor
And,
of 2.
Then you have another ephemeral factor and another geometrical series for the two heavy. So conceptually, how can we I mean, put all this together?
I can actually, I happen to have treated this system, so I can show you the spectrum if you like. I have it just maybe. Do you want me to show it now? Maybe after we first go through the main topic of this lesson, and then we can come back to this point if you like.
Yes, if you are going to show this later, I mean,
I can show it later. If we have time, I can show it later. Yeah.
Okay.
But essentially, this is what you say is correct. So if there's no interaction between these two light particles, then essentially you will get in the Bonner-Penheimer approximation, you will just get a factor of 2 here. You will get twice this ephemeral attraction basically, and you can see that in the spectrum. If we have time, I will show you later.
Okay. So this is one way to decrease the ratio between the ephemeral states in some sense as well.
Yes, in a sense, it's similar to changing the mass ratio. You're right.
Yes.
Yes. Okay, so now let's go to the this one. Okay. Okay. Oh no, sorry, that's not that one. So can you still see my screen? Is it okay? Hello, can you hear me?
Yes, it works fine.
Yeah, it works fine. You can see the screen. Okay,
or
good.
At least for me.
Okay, well, that should be the same for everyone then. Okay, yeah, so today's topic is about the so-called van der Waals universality. So far, we've been talking about the essentially zero range, what I call the zero range universality. And we'll look today at a more specific class of universality that is for systems interacting with van der Waals interactions. And the plan is very simple. First, we'll look at what that means for two-body systems, and then what that means for three-body systems, and in particular for the ephemeral three-body parameter. So let's start with two-body systems. Right, so what we've seen before is that when we have short-range interactions, so however complicated they are, at some point the potential becomes essentially 0. So we have a non-interacting region where the wave function is just a free wave, a linear combination of sine and cosine. And that can be described by just a phase shift at large distance. And this is how it leads to the zero-range universal theory. But actually, there can be intermediate region in this potential between some core region here that is up to some range which I call C, and in between C and the range B of the potential, there can be a region where the potential has a very simple form. It follows a very simple law that is described just by a few parameters. Sorry, that was my daughter. yeah, it's described by just a very simple form that depends just on a few parameters or even just one parameter. And in that case, it's possible to do something similar to what we did before for the zero-range theory, but now with not free wave function, but interacting wave functions. And again, there will be some kind of coefficients here that appears that is sometimes called a quantum defect. And this is something that actually dates back to problems like the electron in a Rydberg atom. So, you know, Rydberg atom is an atom with an electron that is excited to very highly excited states, where the electron goes to very large distances. And at these distances, what the electron feels from the rest of the atom, so the core electrons and the nucleus, is just a Coulomb interaction. So it's very similar to the hydrogen atom. We have the same interaction potential at large distance, but then when the electron goes to short distance and reaches this core region, then it's not Coulombic anymore because there's some complicated interaction with the electrons and the nucleus. But most of the time in the long range region, it's just a Coulomb interaction, and so it means that the wave functions and the energies are very close to that of the hydrogen atom, which would be given by this kind of function f. But then there's a correction that is given by this quantum defect, and this is a simple way to describe the systems without to have a very detailed knowledge of this core. In the same way that the phase shift here represents the what happens in this whole region of the potential, and we can build a zero-range theory by just using the information from this phase shift. We can also design a theory that explains everything that happens in this region and in a wider range of energy by just a single quantity here that describes what happens in the core. So in the case of the regular atom, this Coulomb interaction is a very simple law. It has just a single parameter that can be expressed in a particular length scale. So to do that, you can just equate the potential with the kinetic energy, and that gives you the natural length scale, which is here the Bohr radius, right? Now the same situation, the same idea of this quantum defect theory can be applied to the case of two neutral atoms. And in that case, as I mentioned before, the tail of the potential is as a simple form, which is attractive 1 over R6 up to the 6th power potential. This is called van der Waals tail, van der Waals interaction. And maybe someone has their microphone on. I can hear my voice. So could you please turn off your microphone? Thank you very much. Right, and again, this is a very simple form that depends on only one length scale, and that can be constructed again by equating this 1 over R6 potential to the kinetic energy, and then we get a length scale that is given by this expression in terms of this C6 coefficient, and this is called the van der Waals length. I should mention that it is not called the van der Waals radius, because the van der Waals radius is actually something else. That's something that appears to describe the equation of state for non-ideal gas, and this is the measure of the deviation from the non-ideal gas. That's also, and this is called van der Waals radius. So to avoid the confusion between these two quantities, which are not the same, this is called the van der Waals length rather than the radius. Okay, so now let me explain very simply this quantum defect theory. So we've seen that in the free region, so we have a free wave function that is described by this phase shift. Now this is true for any energy, actually. When we know the phase shift at any energy, we can describe the wave function at large distance for any energy. But what we've seen is that at low energy, so when the energy is smaller than the energy scale associated to this range B of the whole potential, the tangents of the phase shift is approximately equal to minus k times A. And there we have a single parameter, the scattering length, that describes the physics in this low energy region. So the same thing happens in this now this whole region here for R larger than C. They can be described by two independent solutions for this simple law of the potential. So we call them F and G, and the general solution is a linear combination, and the one that corresponds to the proper boundary condition that comes from what happens in the core is given by this this quantity here. And so again, in general, this quantity would depend on the energy, but there's a range of energy where it's essentially constant, and that's quite easy to understand. If we are in a range of energy that is smaller than the magnitude of the potential in this short-range region, then the wave function will not depend on the energy. Which means that the value of this phase will just be will be nearly independent of the energy. And that's understandable because in the Schrödinger equation, when we are in this region, the energy here is so small compared to the interaction potential that we can essentially neglect the energy. And the form of the wave function in this region is essentially the same as the wave function at zero energy, for zero energy. But this is only true in this region where the potential is deep. Of course, when we go in this region here, then the energy is not negligible compared to the potential, and therefore here in this region the wave function is highly energy dependent. But in this region, it's nearly energy independent, and you can convince yourself that actually this range of energy is much larger than this range of energy. So what it means is that we can actually extend the idea of this zero-range theory by including, so having a new quantity to fix the linear combination of the solutions. So that's the same role as this phase shift here. But in addition, now we have a new scale, or perhaps two new scales, depending on the complexity of this potential. Here we have a new parameter. And at the price of adding just one more or a few parameters, we can have a simple description of the wave function without having to know exactly what happens at short distance. So, so here I show this is an example, for example, for a bound state, which is still in this range of energies, where this approximation is valid. Then you see that you have a very different behavior at large distance. Of course, you have a scattering state at positive energy. You have your bound state that decays exponentially at large distance. But in the short-range region, they have exactly the same form of wave function. They have exactly the same phase here. Right. So all the functions are the same in this region, and so. Yes, and so we can just, in the same way that in the zero-range theory, we just forget about what happens here and input a boundary condition for this free wave, we can just have a fixed boundary condition with a fixed phase phi zero for all these functions in this energy range, and that will be enough to describe the physics of this potential. So essentially, that is the idea. It's just an extension of, you may regard it as an extension of the zero-range theory. Right, Right, and again, these functions, this is interesting because this function f and g, they are still relatively simple. They depend only on typically on a single length scale. So if we have a van der Waals interaction, which is the one length scale. This quantum defect here is essentially carries the same information as this phase shift here at larger distance. And at low energy, they're all related to the scattering length. So essentially, the information of this this phi 0 is the same as the scattering length. Its expression will, of course, depends on the choice we make for these independent solutions. And so now I will show you that we can choose some simple, there's a simple choice of solutions. So now let's focus on the van der Waals kind of potential. So, and let's look at the mathematical solution of this kind of potential, minus C6 over R to the 6. So this is the radial equation in the S wave. So here I will just consider the S wave, but you can generalize to higher partial waves. So it looks like this. So the first thing we do is first we put this prefactor with the h bar squared and the mass on these terms. And then we want to have a dimensionless equation. So we introduce some length scale, which is, for the moment, we do not define it. So with these new variables, we have now this length squared, here this length to the power 6. And then we can multiply everything by L squared, and then we left with L to the 4th here, and here we have L squared. So now we can introduce a reduced energy here. Some dimensionless energy, epsilon. And here we want to make this also dimensionless. So we set this length to be given by this this prefactor to the power 1/4. And you see that because this is the power 4, this will cancel. Now, as you see, I have also this prefactor 1/2 here, which is a kind of convention in recent years to define the van der Waals length. And with this convention, the dimensionless equation reads like so. So you have this second order derivative, and here you have potential is 16 over x to the power 6. So you might want, and this 16 comes from this factor 1/2. So you might wonder, why do we have this factor 1/2? Because if we don't have it, we would just have 1 here. Actually, it turns out that in the final results of these equations, the results look better if we have this factor 1/2. All the numerical coefficient will turn out to be closer to 1, actually. It's only in the Schrödinger equation that we have this 16, so it's actually a better choice. And now most people actually make this choice for the definition of the van der Waals length. But of course, that's just arbitrary. Okay. So now let's look more specifically at the solution of at 0 energy. So now I set the energy to 0. And in fact, we can find analytical solutions. So let me show you very briefly. So we can introduce this change of variable. So the radial wave function is given by x, the square root of x times some function v of 2x to the power minus 2. And with this change of variables, so you can calculate the second derivative of u in terms of this expression, and it gives you an expression in terms of this function v. So you have v second, v prime, v, and some prefactors. So now we put this result into this equation, and we also express this u in terms of this square root of x times v. So it's like so. And then let's multiply everything by 1/4 times x to the power 3/2, and we get this equation for v. And now you will recognize in these prefactors, they are just powers of this argument here, which we may call y. And so you get this equation, the simple equation for v, and this is nothing but the Bessel equation for the parameter alpha equals to plus or minus 1/4. And so that means that the solutions of these equations are in general linear combinations of the Bessel function with parameter minus 1/4 and the Bessel function with parameter 1/4. And now if we express it back the original radial wave function, we get this analytical expression. So now we can actually relate this coefficient alpha and beta to the physical quantity, which is the scattering length. So we can consider the two independent solutions, f and g, which are given by this Bessel functions, so minus 1/4 and plus 1/4. And if we put in from these prefactors, which are obtained from the gamma function, so gamma of 3/4 and here gamma of 5/4, then these functions are such that this f is asymptotically goes to x when x is large, and this function g asymptotically goes to 1 when x is large. So then it's very simple asymptotics for these two functions, which means that if we want to construct the radial function out of these two functions, the choice is very clear. We have to write it as f minus the scattering length divided by the van der Waals length times g. And the reason, of course, is because at large distance, it satisfies the definition of the scattering length. That is, that this goes to x, so that's x is r divided by the van der Waals length, and this g goes to 1. And so we see that indeed this goes to something proportional to r minus a, which is the proper behavior of the wave function at large distance for the zero-energy wave function. So this is a very nice analytical result, which actually I will use later. But that's not enough, because in order to solve the problem in the range of energy that I showed you before, we need to know the solution of this potential for arbitrary energy, or at least in that range of small range of energies. Well, there is actually analytical solutions for any energy for this 1/6 potential that was found in 1998 by Bogau. And this is his paper. But the analytical expressions are actually quite involved. As you can see, to define the solution, you have to define many functions. That takes almost 2 pages to write down all the definitions. That involves finding some root of some equation with continued fractions, and it's fairly involved. It can actually be implemented numerically, and Bogau has done it. But then in practice, it's essentially just as easy to solve the Schrödinger equation numerically with this 1/6 potential. In the end, it doesn't matter so much, because we just need to know the results. And the point is that they depend on a single length scale. So even if we do the calculation numerically, the fact that it depends on the single length scale is the important point. That simplifies the description. So that's the situation. So now let me show you the solution of this potential at negative energy. So this is a numerical solution that you can find by just solving the Schrödinger equation. So again, this is the essentially the square root of the energy. Well, of course, I mean, I have to take the absolute value because these are negative energies. And as a function of 1/a, as in all the plots that we've used so far, more precisely, the van der Waals length divided by a. And we have this kind of energy curve. So here, this is, of course, the unitary point where the scattering is infinite. And this is where S-wave bound state appears. This is the S-wave bound state. This is for the S-wave. So it appears to unitarity, of course, and close to unitarity, it follows this zero-range universal law. That is the square root of the energy is proportional to 1/A. So as expected, but then you see very rapidly it deviates from this this zero-range universality, and then it follows a different path. It gets deeper as the scattering length decreases, and then essentially this side here becomes connected to this side. So what happens is that this bound state keeps getting deeper and deeper up to this point where we meet the unitarity point again, and then this state continues. So a new bound state appears from the threshold, and the state goes down deeper, and you can continue for a range of energy that is as long as you are within you have energy that are on the order of this van der Waals energy scale, which is given by this this formula. So it's just the energy associated with this the van der Waals length scale. If you take any potential with van der Waals tail, it will be described in this range of energy by this kind of universal curve that are universal for any potential with van der Waals tail. And if the potential gets deeper, then you will find then deviations for the deeper states. But for the states in this energy range, they will be described by this kind of universal van der Waals curves. So once we know this this kind of we can solve this kind of van der Waals problem, then we can essentially address any physical system with van der Waals interactions. I mean, two-body system. And here I show you an example to show you how it's actually relatively powerful. This is an example that come from experiments with ultra-cold atom experiment with ytterbium isotopes. So ytterbium has actually many isotopes that you can see here, 168, 170, 171, 72, etc. And they can be prepared in these experiments. They essentially have the same van der Waals potential at large distance. This is essentially given by the electronic structure of these atoms, which is almost the same. So we have essentially the same potential. However, the mass of these atoms is different because their nuclei have different masses, right? So essentially, we can understand these systems as simply the same interacting potential, but with different different masses. And so if you solve this this van der Waals problem with a boundary condition that is given by some scattering length or something like that, you can and then you change the for a certain mass, and then you change the mass, then you will see that the scatterings will evolve like this. So you will have a repeating pattern where the scatterings get negative, diverges, gets positive, there's negative again and diverges, and this repeats itself. And for the spectrum of the balanced states, you get also a repetitive pattern where you have at each resonance, at each unitary point, you get a two-body bound state in the S wave that appears, and then another one, etc. And the dashed curves here correspond actually to D wave states. And so if you, so for example, if you fix the, at a particular mass, you fix, for example, the scattering length, and suppose that you know the C6 coefficients, then all these graphs are completely determined by just a single point. And then you can actually make predictions for what are the scattering lengths and binding energy for this other isotopes. And you can see that there's actually quite good agreement with the what has been measured. So all these points here correspond to actual experimental measurements. I should say that in this work actually, that's actually a work that was involved with. It's not strictly 1/6 potential. We also had added some 1/r to the 8th correction to be more precise, but it's a very small correction. So essentially what you're seeing here is mostly the effect of this 1/6 interaction. Yeah, there are a bit more details in these curves, but essentially you can regard it as a very nice demonstration of the power of this simple 1/6 solution to describe the scattering lengths and the low energy bound states of these atoms. Okay, so are there questions about everything I've talked so far?
No, I don't see any questions.
So. No question? Okay. Actually, this is the end of the first part, and then we have the second part about the three bodies. So if you want
Pascal,
to yes.
Maybe I want to ask a question that I wanted to understand a little bit more. Probably I'm missing something. When you have this van der Waals potential very deep, you show the zero energy solution in the beginning, and then with many nodes.
Yes.
And the bound state, I mean, probably the highest excited bound state, also with many nodes.
Yes.
So therefore, there are many states down there.
You're right.
Yeah, I mean, you could see there or in the beginning of your presentation, where you show the wave function.
Oh, you mean this one? Yes.
No, in the very beginning. And then I was wondering, yes, this one.
This one,
and then I was, you can leave the bound state, just to make my quantum mechanical question. I mean, the zero energy state and the bound states, they are orthogonal.
Yes. They are orthogonal, yes.
What I was wondering, let me put my question, that you have many, in this case, it looks like that you have many bound states in the potential.
Yes.
And therefore, your zero energy wave function should be orthogonal to all these bound states. So if you have many bound states, essentially, this will kill the zero energy wave function, because it has to be orthogonal to, I don't know, 20, 30 states. And this will essentially kill the wave function inside the potential. I mean, even if you do not have this repulsion.
Yes.
This is, I mean, even without the repulsion, just because you have a deep quantum well, you have a wave, a zero energy wave function that simply reflects. And then I was a little bit surprised that you just say, oh, they are more or less equal.
So first of all, about the orthogonality, yes, they must be orthogonal, of course. And this, it's not inconsistent with the fact that in this region they have exactly the same wave, almost the same wave function. They're nearly proportional to one another in this region. But then, of course, as I said, at larger region, then they differ completely. And this is where the orthogonality actually occurs. I mean, here you multiply almost the same wave function, but then it becomes very different. And at some point, you see this function here becomes negative, where here it's still positive. And when you compute the integral, you will see that although you get a positive contribution from this short range part, then in the long range part, you will get negative contribution that will exactly cancel and give 0. So, so the orthogonality really occurs in this region.
Just come at the tail.
Yeah.
At this little tail here.
Right. And the orthogonality, you said it kills the, you said, I think that's what you said, right? It kills the wave function or something like that. You mean
yes.
you mean that the probability is reduced in this region? Maybe that's what you meant, or?
Yes.
Yeah, I don't think it's related to the orthogonality. I think it's so indeed it's true, and I will talk about it actually, that the amplitude is decreased. Actually, on this graph we cannot see. We can see even better on the. This was just a schematic graph, but if we look at the exact solutions, yes, these ones, you can see indeed that it's strongly reduced at short distance. And this is, I don't think it's due to orthogonality, but it's simply due to the fact that you have a potential that is very steep. It goes very steeply. It goes down very steeply, and actually this part of the wave function you can describe semi-classically using some kind of WB approximation. So that means that the amplitude of this wave function is related to the classical speed, because classical velocity that the particle would have inside this potential. So since the potential is very steep, when you go down, it's very strongly accelerated in this deep potential, and so physically it means that it spends very short time in this region. It goes very fast, and then the probability is just proportional to the 1 over the, I think it's 1 over the square root of the speed or something like that, the classical speed, if I remember correctly. So yes, so you do indeed have suppression of probability, and that's can be understood classically from classical acceleration.
Yeah, maybe there are many possibilities of interpretation of that, because it looks that you have an infinite number of bound states below the zero energy.
That's right. So that's the other comment I wanted to make that is actually important. I forgot to tell about that. So thank you very much. So this is the solution of the pure 1/6 potential. This is a mathematical solution of the pure 1/6 potential. And indeed, it has infinitely many oscillations. And actually, that's because we are exactly in the same situation as the 1/r² potential, the Efimov potential. It's not, essentially, it needs some regularization at short distance. So if you cannot solve the pure van der Waals potential physically, because the fluctuation of the kinetic energy are not enough to stabilize the system, like in a Coulomb potential, for example. It just goes too fast for the kinetic energy to stabilize. So that means mathematically that we're exactly in the same situation as the 1/r². Actually, any potential which at the origin goes like 1/r to the power alpha, where alpha is larger than 2, you will have this problem. It just goes too fast. And then it means that you can have, you see these two solutions, they look physically acceptable. There's no divergence. So they look physically acceptable, not normalizable. And so that means that you actually have an infinite number of solutions. You can get any linear combination. So there's no discretization of the bound states. You can get any bound state at any energy you want. It's exactly the same issue that we had with the 1/r² potential. So physically, what it means is that it's not possible to have a pure 1/6. There needs to be some kind of something that happens at short distance, some repulsive wall or something that can cure this problem. So mathematically, you can implement that by some boundary condition. You can set a wall or or just start from some non-zero value and then input some boundary condition, and then you will have a well-defined problem with the discretized energy spectrum for the bound states and everything. So this is why you see here indeed there's an infinite number of oscillations, but of course in a real system that would be cut at some distance, at some physical distance, where you have a repulsive wall or something, and you would just get a finite number of oscillations. And of course, if you have a very shallow potential, you can have the repulsive wall can be at much larger distances like this one, and then you have essentially no oscillation. This is the case, for example, in the case of the helium-4 that I showed before. The interaction potential for these helium-4 atoms is very shallow, and it supports just barely S-wave bound states, so there's almost no oscillation in these West functions. But for most of the atoms, in particular the ones that are used in these ultra-cold atom experiments, they are fairly deep potentials with many S-wave bound states. So you would have many oscillations, maybe, I don't know, like 40 oscillations or something like that. That's typical situation. Sorry, my answer was a bit long, but
it was very good. Thank you, Pascal.
Okay. Okay, so as I said, we are at the end of the first part. So would you like to make a short break, or?
So I think if you deem this be a perfect point where the subject split into two, I would suggest that we'll take 5 minutes, 10 minutes break.
Okay, very good.
And then reconvene in, what's the time? Sorry.
It's 5 to the hour.
Yeah, 5 to the hour. So we can.
So let's make it 5 after the hour, and then.
Okay. Good.
Okay. I was typing my comment, but
Yes,
this
I'm reading it now.
no, I can also tell you. So it was really, I think I never reflected that this might also happen or that this is something which is more easily seen in the two-body system. So usually in quantum mechanics, we always deal with Hamiltonians, where the spectrum below threshold is discrete.
Right.
So but that it's actually a signature of a non-compact Hamiltonian or a non-renormalized operator, that I have also a continuous spectrum with energies below zero. And this signifies some inconsistency, some divergence in the theory, which is precisely what this, or what I recall from the derivation of, I think it was Amado and co-workers who related the Efimov spectrum to the diverging trace of the three-body propagator.
Right, yeah, yes, Amado and Green, yeah.
Yeah, so this was something I guess is related to that, but in the case of this diverging, or even in the Coulomb case, I think no. Yeah, you can see a similar thing in a two-body setup, which is much more transparent and easy to identify.
Yeah.
So this was, yeah, thank you.
You're welcome. Okay.
But it's something just out of curiosity, because we still have some time. You mentioned this this rather mathematical proof that there is no Yefimov effect in the four-body system, in the same sense that if you have a zero, so an attraction which is too weak or just puts a three-body state right at zero energy, there's not the same tower of an infinite number of four-body bound states. Based on your personal experience with that, do you see, so for me the proof of that is, requires some knowledge about integral equations, the compactness of kernels, and also some approximations, as I recall it. Do you see any problem with that proof? So is there maybe a loophole in it which still allows for the for this emergence of an infinite series of states? Or do you just personally, is it something you would say this is rigorous and there's nothing which can invalidate?
Yeah, to be honest, I don't remember the details of that. I remember that indeed they analyzed the kernel of these integral equations and as you said, characterize whether there's this precisely this problem of having a not well-defined boundary condition. But yeah, I don't remember the details. I could not tell you whether there's any loophole. I'm not aware.
No, it was just curiosity, because
I trust their result is correct, at least for the hypothesis that they assume that they considered. I think they consider identical bosonic particles, I believe. And that seems to be confirmed by the more recent numerical calculations. Although numerics, you can miss things, especially when you have subtle things like accumulation points of a series of bound states that could be missed experimentally if the energies are very small. But I would I don't know. I believe that I suppose that the results are correct. It would be interesting. I mean, you find that actually that there's a there's some assumed conditions, specific condition that I have assumed that is not true in general, and it could be actually a way to have this four-body homostates with bosons. I'm not aware, but that could be interesting.
They make several comments about their approximations and their justifications, and they also say, or they give detailed arguments about why it happens in for 3 particles or 3 bosons, but does not happen at others. But those are quite nice and geometrical, I think, but they are one sentences, and it's very hard to, or at least for me, to retrace those arguments and see what could change that behavior. But it's, no, I didn't mean to go into that. I was just wondering whether you have an opinion on it.
No, unfortunately, I haven't looked into this that level of detail, so I couldn't tell you, unfortunately. So shall we proceed to the next part of it?
Should be time, and all 24 people are still here, so let's continue with the second part.
Okay. So that we've seen. Okay. Okay. So now I would like to talk about what happens when we have 3 identical bosons with van der Waals interaction. And the central problem we're going to talk about is this problem of the 3-body parameter, which I already introduced to you. And the way we introduced it was in the zero-range theory. This was something that we had to introduce by hand, again, because of this problem of the necessity of having an extra boundary condition to make the problem well-defined, I mean, physically sound, and to quantize the spectrum. So we introduced it by hand. And so in the zero-range theory, it appears like this. We have a kind of spectrum that is originally continuous, but then we introduced an extra boundary condition, a 3-body boundary condition, and then the spectrum becomes discrete. Well, it depends on how you implement this boundary condition, but if it's just a boundary condition at really vanishingly short range, then you can get still an infinite number of, I mean, the spectrum would not be bound from below. But of course, in reality, there is always a ground state. So the physical way to implement this boundary condition is with some kind of something that makes the wave function vanish at short distance, which is the physical boundary condition. So that would always produce a ground state. So we would get something. So we'd get something like this, right? In a real physical system, they would do the ground state, which as it gets deeper, deviates quite significantly from the zero-range theory prediction, and then the excited state would gradually conform more and more accurately to the zero-range theory. And then these zero-range theory states were just unphysical. So you see that this spectrum actually is determined by the scattering and the 3-body parameter. So there are different ways to measure the 3-body parameter. It's one way is to just go to unitarity, where there's no more scattering lengths. It goes to infinity, so there's no more scattering lengths, and then the only length scale that remains is, for example, the length scale associated to the energy of this trimer at unitarity. And then all the other trimers are related by the scaling factor, right? So we just need to specify, for example, the energy of the ground states. But another possibility is to specify the scattering length at which one of these trimers appears from the 3-body threshold. Once you pick you specify one of these points, this point or this point, then you fix the whole spectrum. And if you change the value of one of these points, you will just make the spectrum grow or shrink accordingly, right? But actually, as we said, in a real system, the scale invariance is a bit broken close to the ground state, and maybe also for the first excited states. So really, we really converge to the zero range theory in the limit when we go to this very highly excited state close to this zero energy and unitary point. So one formal way of defining the three-body parameter in a real system, I mean, in a zero-range theory, it's just a parameter that you fix by hand. But in a real system, there's no zero-range theory is just something that's just an approximation. So if you have a real system, the definition of the three-body parameter, the natural definition would be one of these quantities, but in the limit of large, very excited states. So that means that you can define these quantities for each state. So here we have this we call kappa star. Conventionally, this is the binding wave number associated at unitarity associated to these trimers. So kappa star 0 is for the ground state, kappa star 1 is for the first excited state, etc. And then we have the same for this scattering length at which the trimer appears from the three-body threshold. So we call them A minus, so A minus 0 for the ground state, A minus 1 for the first state, and so on. And if we pick any of them and multiply by this scaling factor, then we will always get something of the same order for all these, any state we pick. And if we take the limit when n goes to infinity, that should converge to well-defined value, kappa star and A minus, and that would be the true value or true measures of the of that three-body parameter. So they are equivalent. We can choose one or another. They are just different measures of the same physical parameter, physical quantity. Yeah, so it's called parameter because originally it's something that we put in the zero-range theory, but it's just in the end some kind of physical observable like the scattering length. We just have to define this how from experimental observation how to define it. Well, the problem, of course, is that experimentally you may be able to see a ground state, ephemeral state if you're lucky, but then it's not really quite an ephemeral state. Observing excited states is even more difficult, and then it's nearly impossible to observe this highly excited state. So you cannot reach the true value of this three-body parameter, but you can. So what people do in practice is that they use these values for the ground state as a kind of reasonable approximation of the three-body parameter of the system. But strictly speaking, they're not. We should take the limit for this, the limit of highly excited states. Okay, so that is well defined, and then there comes the question: if we have a real physical system and we know we will obtain this kind of spectrum that will conform to the zero-range theory for very highly excited state. And then we will find some three-body parameter. And then what is the value of this three-body parameter? We know that it's somehow determined by what happens in the system at short distance. That is due to the physical interaction at short distance. But is there a way to actually predict this three-body parameter? The scattering lengths we know how to calculate from the potential. In principle, we just solve the two-body Schrödinger equation. So the three-body parameter, we also know how to calculate it. If we solve the three-body Schrödinger equation, we get these levels, and then we get the three-body parameter. But can we get some understanding about where it comes from in that solution? So what's in the interaction potential determines the value of this three-body parameter. And what we've seen is that this Efimov effect is strongly related to the Thomas collapse. The fact that if the range of the force, the two-body forces is smaller, then we get deeper energy. So it seems that somehow this three-body parameter is somehow related to the range of two-body forces. That very roughly, this the value of this kappa, for example, is on the order of 1 over the B, the range of the potential. But there could be also inferences from three-body forces, right? We could have some result for just two-body forces, but then if we add three-body forces in the system, that would surely change this three-body energy and therefore the three-body parameter. So these are general questions that have been asked for since the Schmorf effect was discovered. And then there were experiments with ultra-cold atoms. And what people have come to realize after obtaining many different results for many different kinds of atoms, so these are essentially all bosonic atoms or boson-like atoms. Like this lithium-6 is actually, I explained before, is actually a fermionic atom, but it can be prepared in 3 different internal hyperfine states. And so they essentially behave like bosons with different scattering lengths, but essentially like they have the wave function as a bosonic symmetry. And what appeared from the experimental data is that if we plot the, for example, this quantity A minus, where the trimer is found to dissociate into the three-body continuum, as a function of the van der Waals lengths for these different species, we find that there's a good correlation, and that roughly the A minus, so this is always for the ground state because that's what is measured, is roughly -9 times the van der Waals length. So then it seems that there's a simple origin for this three-body parameter that is rooted into the van der Waals tail of the interaction. And so that prompted the, well, for the theorists, they need to understand this result. So this has been called the van der Waals universality of the three-body parameter. So there was some early proposal that this could be understood as a result of the phenomenon of quantum reflection. So quantum reflection is something that actually I think it also happens for classical waves. If you have some steep step potential, like some steep potential at some point, a wave can be reflected by the steep dip in the potential. So usually we think that the wave is reflected by a wall, but actually when you have a very deep well, you can also have a reflection. And so for quantum mechanics wave function, this is called quantum reflection. And so the idea was that at large distance, if we plot the effective potential felt by 3 particles, by these 3 bosons, we have of course the Schmorf attraction, 1 over r squared. But then when we enter the region of on the order of the van der Waals length scale, then we have the van der Waals interaction, and that's a much steeper, 1 over r6 kind of interaction. And so that could create a quantum reflection that prevents the wave function from going into this short range region, and therefore it would be only sensitive to what happens in this van der Waals region, and that would set boundary condition that would just depend on the van der Waals length, and that would explain the results. And so to support this view, there's some simple model like this was made. So just Schmorf attraction, and then at short distance kind of square well, like some very deep potential. And if we so then from this potential we can calculate the phase that fixes the energy levels or in this potential. So that's equivalent to the three-body parameter for this 1 over r squared potential. And we can calculate it as a function of the depth of this well. So here is the depth of the well, and here is the phase. And you see that as we make this potential, the square well potential very deep, then this face, it can essentially take any value, but gradually it becomes more and more probable to be around a specific value, like this one, and almost accidental to have other values. So so this looks like a nice explanation for having a well-defined face that it is determined by this.
Pascal,
yes.
may I interrupt you? Can you briefly comment on what sets the frequency or of this cyclic behavior? Is that related to the magic number or 22, or is there anything in the system which allows me to control the, in this case then, the probability to end up on one of those plateaus or being in the large phase region?
Let me think. I'm not sure, but yeah, I think yes, I think this is related to, that should be related also to the levels in this 1/r squared potential. So I believe, yes, that's related to the scaling, although it's not, here we just changed the depth of it. Looks very regular. There's no logarithm involved, it seems here. So, or maybe it's because, I'm not sure. I don't want to say something wrong, so I don't quite remember. But yeah, I mean, it's the usual, situation that we also saw for the van der Waals potential, that when you change the depth of, I was changing the mass, that's equivalent to changing the depth of potential, then you go through this cyclic pattern that you just the boundary condition or the scattering lengths or whatever just repeat itself. But here I think it's a little bit different. I think here it's really this idea that you have this quantum reflection is going on, and that because you see at the beginning it's very very broad, and then it becomes very more definite. So yeah, I think in this case it's a little bit different. It illustrates the effect of the depth of this potential. So clearly there's something different when the potential is shallow and when the potential is deep. When it becomes very deep, maybe there's then it really becomes periodic. So maybe this is related indeed to, although I cannot say for sure now, right now.
Thank you very much.
Because what I wanted to show you actually is the next graph, which is also revealing, is that when you don't use a square wave potential, but you actually use a van der Waals. You don't approximate van der Waals by a square wave, but just you use van der Waals 1/6. So you smoothly connect 1/2 to 1/2 to the 6. And then of course for 1/2 to 6, you have to impose some boundary conditions. So here there's a what you get, a hard wall to get physical results. And if you do so, then you get a completely different picture. That when you as you reduce the location of this hard wall to make this 1/6 behavior stronger and stronger, you see that you don't have some kind of stabilization of this phase to some particular value. It remains completely arbitrary. So so in the end, this idea of quantum reflection does not appear to be relevant here. Okay, so then these people, Jiang Wang and collaborators, they actually solve the problem, the three-body problem, with various kinds of two-body interactions having a van der Waals tail. So they all have exactly the same van der Waals tail, but they have different behavior at short distance. So it can be a repulsive wall, or they can be purely attractive. many different kinds of behavior at short distance, but they can be adjusted to have the same scattering lengths. They can be adjusted, particularly to go to unitarity, and have exactly the same van der Waals tail. And so they solve essentially this three-body problem exactly using the adiabatic hyperspherical representation. Essentially, that's the general form of what we saw when we followed the derivation of the Efimov effect. Is the most general form where you separate the wave function into the hyperradius and hyperangles. So you have we have already introduced the hyperradius and its hyperangle alpha, which is related to the essentially the ratio between the Jacobi coordinates. And then of course you have the angle theta between these two vectors, and that's all you need for rotationally invariant three-body system. And then you can decompose the wave function into you can solve the problem for the hyperangles, and that creates various channels in which the problem for the hyperradius can be solved. So you end up with coupled equations for the hyperradius with different potentials and couplings that come from the solution of the hyperangular problem. And then this can be solved numerically. It's quite challenging, especially for in the study, they used potentials that can support, I think, up to 10 S-wave bound states, so quite deep potentials. So it means that you have an extremely large number of these three-body potential, these hyperradial potentials. Sometimes it's referred to as some kind of spaghetti. You have many of these potential curves. So it's numerically challenging and intensive, but they were able to do it. And what they found is that irrespective of the potential they use, they always found more or less the same results as long as they have the same van der Waals interactions and they have sufficiently deep potentials. And the result for this value of these measures of the three-body parameter, well, for the ground state, it's kappa stars and minus are given by these values, 0.21 in units of van der Waals length and minus 10.7 in units of van der Waals length. So it roughly reproduces what was found in the experiment. It was more like -9, but within the uncertainty, which are quite large, well, this seems to be at least consistent. So this was very interesting results. That's numerically exact result with van der Waals interactions. And then, of course, the question is, so we get more or less the same result as in the experiment. So why do we have these results? And then we can look at the actual hyperradial potentials that they have in their equations. So this is this hyperradial potential is a function as the hyperradius. And so, as I mentioned, there are actually many of such potentials. But in particular, if we zoom in some range of energy, we will find that there's a particular potential, which I call V0 here. Doesn't mean that it's the first one. It's actually in the middle of many other potentials, but one of this potential actually correlates to the Efimov traction. So it exhibits this 1/r² attraction at large distance. So that's where the Efimov effect is exhibited in this hyperradial potential in this formalism. But of course, that's only true at large distance, because at short distance, then the physics become sensitive to the finite range of the interaction. And then what they found is that there's for all the potentials that they considered, there's always the same behavior that at first the hyperradial potential gets deeper than the Efimov traction. So the 1/r² attraction is represented by this dashed curve. So they all get a bit it gets deeper than this film of attraction, and then there's a minimum, and then suddenly there's this repulsive wall that is more or less the same for all. So all the curves that you see there are obtained here for, so this is for Lena-Jones potential. So Lena-Jones is the sum of 1 over R6, which is dominant at long range, and 1 over R2, and a so attractive 1 over R6, and a repulsive 1 over R to the 12th, which creates a core. And so you can adjust the location of the core to have different number of bound states, to have shallow or deep potentials. But however deep or shallow the potential is, they essentially found the same hyperradial potential. And not only for these Lena-Jones, but also for two-body interaction that is purely attractive. So you have 1 over R6 attraction at large distance, and then the potential is always attractive and goes to some finite value, some negative value, for example. That also leads to the same hyperradial potential, like so. So when we see this potential, we understand that this repulsive barrier here sets a boundary condition for the Efimov problem. So here we have the Efimov 1 over R squared interaction, and then this part here provides a well-defined stable boundary condition that sets the face of the wave function in this problem, and therefore sets the value of the three-body parameter. And that's why it's always the same for all these, the same result for all these potentials. And moreover, we see that this repulsion occurs, so this is in units of van der Waals length. So it occurs at about, for hyperradius, which is around twice the van der Waals length. And so we understand from this that there's almost no probability for the behind this repulsive wall. So the wave function is suppressed here. And therefore, there's no probability in a region where the physics would be more complicated, would depend on the short-range details of the two-body interaction, or also on three-body interactions. If there are three-body interactions, they are typically at smaller distances than twice the van der Waals length. So then that's
Pascal.
Yes. Yes.
May I interrupt you with a very naive question?
Yes,
you
please.
said that I don't have an intuition about those hyperradial potentials, but you said that this kind of barrier or short-range repulsion introduces or implies a three-body phase and sets that. Does it also prevent the collapse of the system automatically? So,
oh yes. Yes.
So there is the theory is then bounded from below. This Thomas collapse doesn't happen.
So the Thomas collapse is due to the fact that this 1 over R squared interaction goes down to 0 basically, and then it's not well defined. But you see that the 1 over R squared actually stops around here, and then it's not 1 over R squared anymore. It's something else, and then there's a repulsion. So from this, you're completely safe from this this Thomas collapse from this point.
Okay, thank you.
So not only it prevents the Thomas collapse, which we knew in the first place it wasn't physical. We knew that some physics should occur in this region, but we had no reason a priori to believe that it was a universal. That there could be many different kinds of hyperradial potential depending on the system that you consider, and even if they all have the same 1 over R6 tail in the two-body interaction, they may have different short-range physics, different repulsive cores or whatever, and that could create many different situations in this region. So they would all prevent the Thomas collapse, but in many different ways that would set completely different three-body parameters. But actually, it's not like that. They all give more or less the same curve, and they all set more or less the same three-body parameter. So that's quite remarkable. And they also prevent the influence of three-body forces. So this is really remarkable. And so then the remaining question is, why do we have this repulsive walk here? And in particular, why is there a repulsive wall? Even if we have, I mentioned, even if we have purely attractive two-body interactions, purely attractive, then you will get this repulsive wall like this. So it really comes from the van der Waals attraction, the van der Waals, the 1/R6 attraction. It doesn't come from some shorter repulsive core in the two-body interaction. It comes from actually from the attractive part of the long-range attractive part of the two-body interaction. So how can it be? And then so this is the question I ask here. And then it turns out that it comes from the two-body wave function, and in particular from the fact that this two-body wave function also has this van der Waals universality that we saw in the first part of the lesson. So here I plotted this two-body wave function. We've already seen this function actually. That was the function G that we've seen before in the first part. This is the function that is relevant for the unitarity. So when you have an infinite scattering length for a potential with a van der Waals tail, you get this. So this is the analytical solution that for an infinite pure 1/R6 potential. So this is this dashed gray curve here. This is a pure 1/R6, and the corresponding wave function is this black curve. So this is the here it is. This is the analytic expression that we found. But actually, whether you can have a very deep van der Waals interaction like this, or you can have some repulsive core, even a repulsive core that is very, very strong like this one, and that does not allow oscillation in this wave function. So this is the red curve here. This is the wave function corresponding to this potential. So it has a van der Waals tail here, but then quickly there's a very strong repulsive core. This is similar to the interaction potential for helium-4 atoms, which is very shallow. But you see that even for this this potential, the wave function is actually quite close to the one that you get for very deep potential, because in this region here, the shape of the wave function is driven by this van der Waals tail here. So there's a kind of reduction of probability, and as we saw before, it's related to the fact that the atoms are accelerated, so probability is diminished. And then in the case of the repulsive core here, of course, the repulsive core completely suppresses the probability, so it goes to 0. But in the case of a purely, a very, very deep van der Waals attraction, then we have these oscillations, of course, but they are also very quickly damped by this quick acceleration from this classical reduction of probability due to the large speed of the particles. So in the end, even though you have some structure, oscillative structure, it's very small, and it doesn't differ much from what you get from a repulsive core. So so the final result is that whatever you have at short distance, as long as you have this 1/R6 tail, you essentially get the same shape here, and then in this region you essentially get 0 or very small probability. So that means that this two-body wave function is as a kind of universal character, and in particular, important point to keep in mind is that once the distance between two atoms is smaller than the van der Waals length here, the wave function is almost 0. So no probability, almost no probability of finding two particles in this region. So now if we use this knowledge, we can look at the consequences of this fact on the three-body wave function. So as remember, the three-body wave function is determined by these two distances r and rho and this angle theta. So these two distances can be parameterized by the hyperradius and hyperangle. So here I show a plot where I represent all the possible, three-body configurations as a function of the hyperangle and alpha and the hyperradius. And this is for a fixed angle theta of pi over 2. So this is just to illustrate. I mean, we could have a larger plot with theta, but that would be a three-dimensional plot, so it's a bit messy. So I'm just showing this this section for theta equals pi over 2. So then we can represent this different configurations. So of course, as we increase the hyperradius, the size of the system increases for a given geometry. And as we change the hyperangle alpha, the ratio between R and rho changes. So we go from an elongated configuration for small alpha to a flattened configuration for alpha close to pi over 2. And then we can essentially draw around each particle some kind of sphere with a radius half the van der Waals length. And we look in among all these configurations, the situations where the sphere touch each other, that means the two atoms are within 1 unit of van der Waals length away from each other. And as we've seen, these configurations, I represented them in this red area, they have very small probability simply because of the two-body physics, because of this two-body wave function is essentially 0 here. So so we can expect that all these three-body configurations are suppressed. Now you see that as we reduce the hyperradius for this three-body system, so here at large hyperradius, essentially all possible configurations are allowed. But as we go to shorter and shorter hyperradius, close to twice the van der Waals length, we see that suddenly there's a strong restriction on the possible configuration. Essentially, when we reach this point, only the equilateral configuration is allowed from this restriction. So what it means is that there should be a strong, the wave function has to deform to localize to this configuration. And that means that there's some energy costs, some kinetic energy costs associated to this deformation. And this is precisely the meaning of this hyperradial potential. Remember that this potential are the eigenvalues for the hyperangular problem. So this energy really represent the deformation energy, how this configuration, independently of the size of the hyperradius, how do they move, how do they deform, these three particles deform with respect to each other. And here in this region, we have very high energy, and that's precisely because the system has to deform, and that's explained because of this suppression of probability that can be understood at the two-body level. Okay, so it's a little bit complicated story, but hopefully, I hope you understand this mechanism.
Pascal,
yes.
may I test my understanding of what
yes.
you just described by
yes.
Just conjecturing what would happen if instead of having this steep change of the two-body potential in one direction,
yes.
I would introduce a short distance behavior which still regularizes, renormalizes the system, but now introduces a classical fast acceleration followed by a deceleration, again followed by an acceleration. So something which fluctuates between being very attractive and repulsive.
Some kind of oscillatory potential at short distance, you mean?
Right.
Okay.
So that would, to my understanding, invalidate this argument. This would allow for the localization of particles in a certain distance. And therefore, I would at least reduce this strong hyperradial repulsion and allow for a more higher probability to find all three particles close to each other.
I would guess so, yeah.
Okay, no, then I but this was nothing ever tested, or it's not of physical significance, because this weird oscillatory behavior close to close to zero separation is something quite artificial.
Well, you can actually use a very simple example, which is a square wave potential. So if instead of for the two-body interaction, instead of a 1/6 interaction, you take just a square wave potential. That's a bit academic, but it's a valid short-range potential. But then in the square wave potential, there's no reduction of probability. The amplitude is always constant, right? So in that case, you wouldn't have this reduction of, if I go back to in a square wave potential, you would have essentially the wave function would be just one, at unitarity, it would be just flat. And then you would have oscillations in the square wave potential, and with a flat envelope, right? So there wouldn't be any strong suppression of probability like we see here for this van der Waals potentials. So they would be completely different, and you would not have this configuration would be much more probable, much more accessible in this system. So that's a counterexample. Doesn't work for the simple potential like that. So again, this is very specific. We're really talking in this lesson about van der Waals systems. Although you can generalize it to other short-range interactions, I don't have slides about that, but you can generalize this idea. If you have some potential that somehow suppresses the probability at short distance in the two-body sector, then you can extend this kind of arguments as well. But let's focus on van der Waals interaction for the moment. Yes, so now I hope you can have some understanding of why we have this three-body repulsion that sets the three-body parameter. It originates from this suppression of probability that is a fact of two-body physics with van der Waals interactions. So that's the intuitive understanding. And then in this paper with my collaborator, we tried to check this simple understanding with some simple ansatz. So if this idea is true, then that means that, for example, we can use we can construct a hyperradial wave function. Sorry, a hyperangular wave function. This is a hyperangular wave function that is constructed from the hyperangular wave function that you get in the zero-range theory. So I don't know if you remember, but at some point when we derived the Efimov effect, we obtained at unitarity, we could obtain an analytical expression for the hyperangular part of the wave function, so that we know analytically. And so the eigenvalue of this wave function gives the Efimov attraction, which is purely 1/r², like this, right? But now let's use this and then multiply by a product of pair correlation, where the correlation is simply given by this two-body wave function I showed you before. So this function here, which I call phi, or this one, yes. So this is kind of analogous with the so-called Jastrow correlation product that is used in Monte Carlo calculation or many different. And so the idea is to build some two-body correlation from the van der Waals two-body interaction that is not present in the zero-range theory, and to see if that's enough to understand what happens. And indeed, from this constructed hyperangular wave function, you can actually calculate the hyperradial potential, and you get this blue curve like this. So you see, it's not in perfect agreement. It's just a simple model, but you see that it reproduces very well the the deviation from the Efimov attraction at distances close to the van der Waals length. And then it reproduces a repulsive wall at short distance that is not quite at the same location as the one that is found as exact calculation, but essentially it confirms that qualitatively what happens because of this pair correlation, so this suppression of probability in this region. And then the second ansatz that we considered is the use of separate potential. I think in the first lesson, I think I introduced this separate potential, right? That was in the extras of the lesson, but I think we had time to talk about this. Is that right? I forgot actually. I remember I made the slide, but I forgot if I presented that part.
So at least I remember something when you talked about this kind of form factor and. Yes,
I did talk about it. Yes, so so I said that separate potential is very interesting because it's essentially it has the same simplicity as a contact interaction as the zero range theory, but you can actually include finite range, and this is precisely what we can do here. So we set up a separate potential that has a coupling constant and some form factors. And we choose the coupling constant to be and the form factors to be given from the 1/6 potential and the solution of this 1/6 potential at zero energy. So this function phi again, and so we define them this way. And if we define them this way, actually we can show that this potential, the separate potential, reproduces exactly at zero energy this wave function, the solution of the 1/6 potential. And this is actually very trivial to show. So let me show you. Suppose that we know this zero energy solution for the true potential, for the van der Waals potential at zero energy. So it satisfies this equation, right? Now we'll see that this is also the solution for the separate potential. So if we simply apply this Hamiltonian now with the separable potential onto this state, then we use this definition, and then of course we have this expression. And now we can immediately see that we obtain from this projector here, we obtain this number, and this is just the same as this number, so they cancel out. And then what remains is this term, and then this is just the same as the equation for the original potential. So that's zero. And so that means that indeed this is also a solution for this separate potential, but that's only at that particular energy. Of course, for other energies, they will be different because there are different potentials. But this way we managed to do something very interesting. We have a much simpler potential. That's something that is separable. So it's just as easy as a contact interaction, essentially. And it reproduces exactly the zero energy two-body wave function of this given potential. So that means that we do reproduce this suppression of probability at short distance at zero energy. And actually this works. The near zero energy states are essentially the same as the one as the 1/6 potential. It's for significantly different energies that the results become different. So again, if we believe that the physics can be explained by this suppression of probability in the low energy two-body wave function, then this potential should exhibit the same physical properties at low energy. And indeed, this is what happens. Okay, so I already said that. So the separate potential is an approximation that reproduces exactly the zero energy two-body wave function of the true potential. So that one. So now we can use this separate potential to solve the three-body problem, and it's much easier than solving the three-body problem with actual van der Waals interactions. So maybe I can go very quickly. This is just essentially the same. This has the same structure as the zero-range theory, the Skorniakov dermatization equation that we saw before. So we saw them for for contact interaction or better Paris condition, but it's actually the same when we have this separable interaction. So here, this is just the solution. This is just showing an equation for general separable potential. And we can, because it has the projection of the wave function, we can define this quantity f that are just a function of one of the arguments of the wave function. And so this is the definition of f. And then we get the wave function that is expressed in terms of this f. And combining the definition f and this form of the wave function, we get something that looks very similar to Skorniakov-Telma-Tirosian equation, integral equation, but now it has this form factors inside the integrals, and that so it's not a contact interaction anymore. It's really a finite range interaction, but it has the same simplicity as the zero-range theory. We replace the wave function of two arguments by just a function of one argument. So it's actually very easy to solve. Now, let me first show you how we can get this this hyperradial potential. So suppose that we have solved this integral equation. So then we know everything. We know the wave function in momentum space like this, right? So we have determined this f numerically. So then we can determine the full wave function like this. Then we can do a Fourier transform to go back to coordinate space in terms of this Jacobi coordinates, rho and r, and the angle theta, or in terms of the hyperspherical coordinates, r and alpha. Now, if we consider the normalization of the wave function, so in this coordinates, we just integrate over the vectors r and rho. And if we, so that means integrating over the distances r and distance rho and the angle theta, so something like this. And if we go to this hyperspherical coordinates, then we have this kind of integration for the norm of the wave function. And this tells us that the integrand that is inside the integration over the hyperradius is actually the hyperradial probability density. That's what you obtain when you integrate the wave function over all the hyperangles and angles. That's just a function that depends on the hyperradius, and that's the hyperradial probability density. So this can be interpreted as the square of some wave function f, of an effective wave function f, that would satisfy an effective Schrödinger equation with an effective potential W, hyperradial potential. And so if you just invert this Schrödinger equation to determine the potential such that this Schrödinger equation is satisfied, then you get that the effective potential is the energy plus the second order derivative of this effective function f that you found here numerically divided by the function itself. And that gives you this red potential. And so you see that it's quite close to the exact potential obtained for true van der Waals interactions. And then finally, you can check that you get the same physical results. So here, this is the three-body spectrum that you obtain from this separable interaction. So at negative energy. So we get the two-body bound states. So close to unitarity, we all, of course, it satisfies the zero-range universality. So it becomes follows this line here. That's the universal region. Then it deviates, and then you see. So this is the black curve here. This is the result of several potential, and this long dashed curve here is the exact result for van der Waals interaction. So that's the curve I showed before, and you see that they agree well within a wide range of scattering lengths. Eventually, it deviates, and then it has an unphysical behavior like this. But in this range, it reproduces very well the two-body van der Waals two-body bound states. And then the red curve is the trimer state obtained from this integral equation for the separable potential. And from that, we can extract the So unfortunately, I didn't show the exact result for the van der Waals the three-body problem with van der Waals interaction. But essentially, it agrees very well in this region, like the two-body bound state, and then there are some deviations around here. And then we can look more precisely at the values we get for A minus and kappa star. And there are these values, so 0.187 for kappa star and minus 10.86 for A minus. And that's very close to the results that were obtained with full calculation, exact calculation, numerically exact calculation with the van der Waals interactions. So this confirms that the pair correlation, and in particular this reduction of probability, the two-body level is the key to reproduce this these three-body universal results of the three-body parameter. Okay, so that was actually the all I wanted to tell you about this van der Waals universality. So I now come to the conclusion of this lecture. So, well, my conclusion is very simple. I hope you you could understand that well, this universal two-body physics is well, it has been a developing field of quantum two-body physics. So as you could see, both theoretical, there are many theoretical developments in prediction, but also experimental confirmations, especially thanks to atomic physics and ultra-cold atoms. And with this new interest, we found a whole collection of universal two-body bound states that may be relatively rare in nature because they require some accidental condition, but once these conditions are met, they have very universal properties that are quite remarkable. So if you're interested in more details, I invite you to read, for example, these recent reviews. This one by Green, Janikas, and Perez Rios. That was published in Review of Modern Physics. And this is our own review paper with my collaborator, Shibe Endo, that we published around the same time. Okay, so I think this concludes this lecture. So if you have questions, please.
Thank you very much, Pascal. This was, I think, a very encouraging and insightful last lecture. I think there is at least one question by Tobias.
Alejandro, I think Alejandro can start. I already made a lot of questions after Alejandro. If Pascal has enough energy, we go.
Pascal, in your last transparency before the conclusion, you showed these values of A0 and K star.
Yeah.
Yes, here. And if you look to the product of both, which is independent of van der Waals lengths, the number is around -2.
Yeah, yes.
Also for the, and this is a very independent model result that can be obtained also with a completely different characterization of the universal window. I will show this afternoon.
Okay,
so
very good.
It's very interesting that the product is almost because cancel the lengths can be obtained also inside universal window using completely different length scales.
Yes, that's right. That's a universal result actually that occurs for all the excited states, and it's. I would say, however, that for these are the results for the ground states. The ground state deviates a little bit from the universal theory, so these values themselves they may have some deviation from what you would have for the highly excited state. But the product of the two might be indeed relatively close to the universal prediction. It might be a little bit different. I'm not
it's
sure.
It's a little bit. No, I have it.
You have the value?
Yes, it's a little bit bigger than in absolute value.
Right.
But if you look at different levels, the tendency is to go to the exact value. I will show this in my lecture this afternoon.
Okay, very good.
Maybe me, Johannes.
Yeah, Tobias, please. I wasn't.
Yeah.
Don't be
Indeed.
shy.
No, just I asked a lot. I mean, Pascal, this is two questions. The first one is about what you just are discussing. And then the second one, I want to go back to the Bohr-Oppenheimer, because I think we didn't clarify everything. But first, I would like just to point out something that surprised me, and is about this van der Waals universality that you already comment that in some special cases I think when you have narrow Feshbach resonance, you can deviate from this beautiful result.
Right, yes. Yeah, I decided not. Yeah, I decided not to talk about that because then that would be too long. So I just
but just a general idea on that.
Yeah, so that's true. Indeed, everything so you could see the theory I showed was just for a single interaction between at the two-body level, just a single potential describes the interaction between the particles. In reality, in these experiments, they are obtained using these Feshbach resonances. So you have actually coupled potentials. I mentioned it in the first lecture, but I didn't go through the details. But you have a coupling of different potentials that creates that makes it possible to change the scattering length. And then, indeed, these Feshbach resonances that result from this coupling, they are different kinds. So there's one kind which is, well, there are, say, two limits. One limit which is the broad, or more properly called the open channel dominated resonance, and then the narrow resonance, which is more appropriately called the closed channel dominated resonance. Essentially, the broad resonances, they can be described by effectively by a single interaction. So this is what we did here, actually. So that's why what I've shown here works, because we can describe them by this broad. So most of the results we've seen, they were actually obtained for broad resonances. That's because they are experientially the easiest to observe. They're broad, so they're easy to find and use. But in fact, indeed, if you solve the three-body problem with narrow resonances, then situation is a bit different, it's actually quite complicated. And I think, in my opinion, it's not completely understood. One limit that is well understood is the narrow resonance limits, and it's a completely different story. Then there's a emerging length scale that is related to the widths and the very small widths of this resonance. This is usually called R star, and this R star is a new length scale that has nothing to do with the van der Waals length scale, and it's actually much larger, and that determines the three-body parameter in that limit of narrow resonances. So that's another universal limit that is not the van der Waals universality. That's another. And then in between, the situation is quite complicated. Both the van der Waals length that is relevant for broad resonances and this length R star, which is related to the width of the resonance, they both play a role, and possibly other length scale might play a role as well. So it's quite complicated. But for this lecture, I just focused on essentially the broad resonances that can be described by that essentially governed by the van der Waals theorem.
Okay. No, it's good to have this perspective. No.
Yes. Oh, yes.
I mean,
and as I said, I think it's not completely understood. I mean, there's been several works on that, but there's not a general understanding, I think.
Okay. So this is nice. So is it still open?
It's still open, yeah.
Yeah, that's nice. And the second point is just about that example, two heavy, two lights that don't interact. It looks, for this example, that you have the Efimov cycle, the three-body cycle,
yes,
and a four-body cycle. How we can
let me show you.
Conceptually.
Okay, I will show you because I actually have the spectrum, have calculated the spectrum. So
if you could comment on that, no?
Yeah, let me show you. So I think yes, I will. Let me try. Let me share a new file, which is this one. Yeah. Can you see the new slide?
Yes, we can see.
So you're talking about this problem, right? Two heavy and two lights, two heavy particles and two light particles. And so in general, there's an interaction between this light, but let's look when the interaction is zero. So let me skip these slides. There we go. So this is the spectrum. So here we have I use a very large mass ratio to really see the effect you're talking about. So we have very heavy particles interacting resonantly through the S wave with very light particles, and there's no interaction between these light particles. Then what you would expect is that each of them will mediate the Efimov attraction. I mean, this Born-Oppenheimer 1/r² attraction, right? And since there are two of them and they do not interact, then it will just be the sum. So here's so I actually solved the Jakubowski Faddeev equation for this system, and this is the results. So this is the spectrum, again, as always, as a function of 1/r the scattering lengths, the scatterings here. So we have we recognize, of course, the dimer, the trimer, the Efimov trimers. So they have the usual scaling that is due to this for this mass ratio, right? So very dense spectrum because of the very large mass ratio. And then you have the tetramers, so the two heavy and two lights, and these are the green curves. And here you can see there's also a dense spectrum like this of state, and with some scaling. And this scaling, if you so here this is three-body, and here if we zoom in this region, you can actually use the Born-Oppenheimer potential for a single particle and then multiply by 2, and then you can calculate the spectrum, and you will see that it matches. This is this red dashed curve, dashed line. They really reproduce this. So you really have the scaling of twice the Efimov potential that you have for the trimers. And now what's interesting is that actually, oops, sorry. There should be another graph. Yes. And what's interesting is that actually these are true bound states, tetramer bound states, but then they survive in this trimer plus one particle continuum as resonances. So in this region, you have a mixture of two different scaling. You have the three-body scaling, I mean the scaling for the one Efimov potential, and you have the scaling for twice the Efimov potential. They integrate and create various kind of avoided crossings. So I think that this is what you were talking about, right? This kind of double scaling. I mean,
yes. I mean, because you have two cycles. I mean,
yes. So you have this cycle here, and for the tetramers, and the cycle for the trimers, and they actually, mix together in this region.
So you have two, maybe in some way, independent cycles. Of course, I mean, if you make this with a potential, I mean, there will be just one, let us say, one scale, but in general, you could move, these two cycles, maybe relatively, no?
Oh yeah, yes, of course. If you change, I mean, There's I didn't specify, but there's of course in this particular calculation there's some cutoff to describe the three-body parameters. So if you change the three-body parameter, you will see these levels will move, of course, and also these ones. So
but in addition, if you have a short range four-body force, you could move the other.
Oh yes, if you had a
four-body
force, of course, yes, of course, yes.
Yeah.
Yes. So then you could.
This is something that is related. Let me before Emmanuel, that I think this is a very interesting discussion. That when we have these narrow resonances, I mean, because of the coupled channel, as you mentioned, it's complicated. But in general, we could have many body forces, in principle, no?
You're talking
that
about
are not easy to derive.
You're talking about two-body narrow resonances, right?
Yes,
Yes.
When you have this in the trap, and then you have the two-body Feshbach resonance, this is a coupled channel. You have the two channel.
Yes.
And then when you go to the three-body problem, to the four-body, I mean, to the three-body system, to the four-body system, you can have, because of these two channels, you can produce, if you want to rewrite your equations, your Schrödinger-like equation in a single channel, you need multi-body forces.
That's interesting. Yeah, that's interesting, actually. So I understand. So people have done works with three-body systems with coupled channels with Feshbach resonances, but I'm not aware of four-body systems with Feshbach resonances with coupled channel interactions. So so that's interesting.
I'm just thinking. I never wrote that. I mean, I just looked a little bit.
I mean that must be quite complicated. So you're claiming that there would be some multi-body force coming from. That's possible indeed. Indeed, there was a recent paper by Prikupenko and Petrov, and where they looked at the three-body force that is generated by this Feshbach resonances. Yes, so probably that's related to what you're saying, and so so you can have a look at this paper, because I think that's related to your idea.
No, I will check.
And then maybe one could do the same for four bodies. That would be interesting. I don't know if it's tractable, but that's interesting. And maybe you can get the four-body force.
This is what I was on, because then maybe you could see a theoretical way to disentangle the two cycles, the Asimov cycle and this Tetherman cycle.
I see. Yes. Okay. So I see. Interesting.
That's
okay. Okay, thank you.
Nice point. Thank you. Now there is Emmanuel. Can you, Emmanuel?
Yes.
You see Emmanuel somewhere?
I don't.
Hello.
Hello.
You hear me now?
Yeah, I can hear you.
I was wondering about, the validity of this 1/R6 potential at short distances, because in principle, this should be valid at longer distance. But if you make the distance too short, you should have other effects.
Yes, absolutely.
For the Coulomb potential, it's known that if you make the distance too short at some point, you have, this is not valid anymore.
Yes.
You have to use, for instance, you cannot treat your particles as point-like particles, for instance.
You're talking about this kind of So here I use the wave function for pure van der Waals interaction, and as we discussed, there are many oscillations, etc. But you're right. At some point, this becomes unphysical.
Yes, this is my point.
Yeah, absolutely, you're completely right. Actually, that's what we were discussing with Johannes before. That you really need that physically. There's something else happens. So typically, you have a repulsive core or something like that, and that completely changes these oscillations. Yes.
Okay, maybe you discussed it before. I missed your other lectures because I had to listen to another conference.
There's no problem.
So I was only wondering about this point.
Yeah, no, your point is very important because otherwise this this wave function is not well defined. So yes, we need such kind of treatment at short distance. Here in this particular calculation, it doesn't really matter too much, but actually, yes, you're right. If you use this wave function, this analytical wave function that has infinitely many oscillations at short distance, actually you find some divergence. For example, if you try to construct the separable potential I showed at the end of the lecture that reproduces this wave function, there's actually some kind of divergence that is due to the fact that you go to infinity here. So in practice, you need to impose some kind of cutoff at some distance, and then you can get nice converged results. So that really shows that indeed this is not complete. This is not physical. This infinitely many oscillations. That
okay, thank you. This was my point.
Yeah, you're absolutely correct.
Okay, thank
you. So, are there any other questions which you want to ask? So, some junior people get preference, of course. No one? In that case, I think I exhausted my quota already, although I still have a lot. But Tobias, do you want to?
Yes, I just want to thank, Pascal, in the name of the organizers, for this great set of lectures. And it's very fortunate in one side that we recorded and we have all this material. This is really a very good didactical material. I will recommend to my students. So I really want to deeply thank you, Pascal, for this. I know that this is a huge effort to organize, all this set of lectures. And I think, I hope to see you in maybe in the next
in the near future, hopefully.
Yes, and we can discuss more. It was very inspiring what you have presented to us. And I would like also to thank Ioannis, to conduct firmly the session. So I would like to thank you also. Okay, so we all see each other in about 1 hour and 40 minutes for the lesson of Alejandro, and after that, Dorte. So thank you very much.
Thank you very much. It's been a pleasure. It's been a pleasure, and I'm very grateful for the invitation to give this lecture. Thank you very much, and thanks to all the people who attended this lecture. Actually, and I really enjoyed the questions, and that was very nice. Thank you very much.